Alright, so this time I want to look at reactions that are not double replacement. We've talked about that. I did another video on that one, but I want to look at, in this video specifically, single replacement reactions and how to figure out if there's a reaction there. So for an example, let's say we have aluminum and nickel 2 sulfate, so NiSO4. Alright, so nickel 2 means it has a +2 charge, sulfate, has a -2 charge. And we want to know if this is going to make a reaction. Well, what you do is you look on your activity series, and if this metal that's off by itself is higher on the activity series than nickel, that means it can actually come in and replace nickel, and nickel will be kicked out. They'll kind of switch places. In this case, aluminum is higher than nickel is on the activity series, so aluminum will come in and replace nickel, so nickel will be by itself. Now here's the thing, you have to remember aluminum does not have the same charge as nickel. Aluminum typically has a +3 charge, so if aluminum has a +3 charge, sulfate has a -2 charge, you are actually going to have to do one of these numbers. Okay, now it will be equal to 0. And then lastly, you have to make sure everything is balanced. So we have three sulfates, so you have to put 3 here, which means you're going to have to put 3 nickels and then 2 aluminums, and now it's balanced. The way we know that this was indeed a reaction is because aluminum was able to replace nickel. If it wasn't, then it would be no reaction. So for another example, look at silver reacting with copper 2 nitrate. So copper 2 nitrate means we're going to have 2 nitrates because each nitrate is -1. In this case, if you look on the activity series, silver is 2 spots below copper, which means copper could replace silver, but silver can't replace copper. So in this case, you would write no reaction. This one mistake I've noticed on single replacement reactions is a lot of you are looking for precipitates. The way you tell if a double replacement reaction is actually a reaction is the formation of a precipitate. For single replacement, you don't have to make a precipitate, so don't use the solubility rules for single replacement. The last type I want to look at is your bromine reacting with potassium iodide. Now you'll notice this does not have a metal by itself, this is a halogen. Well, halogens can replace halogens. They cannot replace metals, so bromine would not, in this case, replace potassium. The other thing is when you have things like up here, the metals replace the metals. They're not going to replace the anions. So metals replace metals, halogens replace halogens. And the activity series for the halogens is the same as it is on the periodic table. So on the periodic table, fluorine is on top, then chlorine, then bromine, then iodine. So remember, they're all diatomic. So fluorine can replace any of them, iodine can replace none of them. So in this case, bromine is above iodine. Iodine is not above bromine, so this can't happen. So in this case, you're going to make KBr plus I2. Now remember, it has to be KBr because bromine's -1, potassium's +1. You're not going to have KBr2. So in this case, we have to balance, and you balance simply by going like that. And that is indeed a reaction. So I hope that helps clear things up on single replacement reactions. And we'll have more coming up with combustion reactions. We'll do some empirical formulas from combustion analysis, and I'll talk more about combustion then.